Hello, we are the Zeus. Don't get sick. Team, conducting a capstone design project on predictive maintenance of industrial robotic arms. Here's the table of contents for today's announcement. We'll start with an introduction, giving a brief overview of the project, and introducing the team. We'll go through an overview of the system that defines and solves the problem we've chosen as the subject of our project, followed by the development process, results, and evaluation, and conclusions. Please pay close attention to the fourth part of the design and development process, as this is where we will discuss our progress. An introduction to our team name. We chose the name Zeus. Don't get sick. Because we want our industrial robotic arm, Zeus, to be able to predict failures in advance through a technology called predictive maintenance, and to prevent Zeus from getting sick from failures. In this way, our project aims to keep the arm healthy and ensure a reliable operation. Our team consists of the following members. First, our team leader, Sang-Min Park. He was in charge of overseeing the project, training the AI model, and extracting weights. Next, team member Da-Hee-shin was responsible for data collection and preprocessing and operating the FPGA board. Team member Sung-Gun Cho operated the manipulator and trained the AI model. Team member Dong Chung-Tuan was responsible for manipulator, operation, and data preprocessing. Finally, team member Na Young Kim was responsible for manipulator, operation, and FPGA board operation. This part is problem definition. In recent years, industries, including manufacturing, have been aiming for smart factories. Industrial robots in these smart factories are an essential part of automation. Therefore, the management of robots is very important. Industrial robots experience sudden failures due to damage caused by wear, cracks, defects, and performance resistance. The table below shows the average cost of downtime by industry. You can see that the cost of loss is high in manufacturing industries, such as steel, casting, and automotive. Therefore, failure diagnosis and prediction technologies are required to reduce costs. Predictive maintenance can help you take action before a production line fails, and can include indirect failure prediction, anomaly detection, and useful life prediction. Predictive maintenance research is also actively underway to detect anomalies in advance. As shown in the graph on the right, the system has a flow chart, as you can see. A sensor board attached to an industrial robotic arm collects data, as shown above left. The collected data is used to adjust hyperparameters, train the AI model, and extract weights. Here is a flowchart of the model's inference on the FPGA. The data collection from the industrial robotic arm, on the left, is the same. However, the weights extracted earlier are applied to the FPGA to perform anomaly detection on the data being collected in real time. So the model infers if the data is normal or abnormal. Next, the design and development process. Please pay close attention to the details. Here's how it worked. We selected important tasks and set the duration to match the difficulty level. We allocated a lot of time to apply and validate the model. The robot arm motion implementation is shown below. Based on the motion flow shown on the right, we set up a pick in place that traverses 4 zones. The acceleration values were collected by attaching to the second axis of the manipulator, as shown in the image below. Here is the data we collected. The graph below is a graph collected from the IMU sensor. If you look closely, you can see that it looks something like the top right. Here is a graph collected using the sensor board. You can see that it is simpler than the graph collected with the previous IMU sensor. Next, we generate error data. Based on the paper on the left, we generated the 4 graphs shown on the right. To elaborate, on the left is the normal data collected. Based on this normal data, we augmented the data by generating the drift, hard over, erratic, and spike error data shown on the right. These data were copied into 100 copies of the normal data, and 100 errors were generated with random locations, random sizes, and random lengths to match the characteristics of each error data. We then merged the 100 generated data into one, and split it into training and test data in an A to -2 ratio. The training data was then used to train the LSTM model, and the labeled data was trained to detect anomalies. On the left is the structure of the LSTM model, and on the right is a graph showing the decrease in loss during training. We also converted the trained H5 file into a header file, so that it could be applied to the hardware chip. The converted header file was applied and used as a parameter within the FPGA board. This enabled AI inference in hardware, and the performance was verified by comparing the model inference results on the PC and the model inference results on the FPGA. The results and evaluation part. The performance metrics were based on the confusion matrix below. The confusion matrix is a matrix that shows how accurately the predicted value predicted the true value. It allows for an objective evaluation of performance based on whether the actual value is true or false, and the inferred value is true or false. The performance metric is evaluated based on the four criteria below. However, false positives in predictive preservation, which can result in loss of life and property, should minimize the number of cases where an anomaly actually occurred, but was not detected by the model. Therefore, the importance of the recall metric, or TP, which is the percentage of actual positives that the model determined to be positive, should be emphasized. Next up is learning progression and adjusting hyperparameters. We trained on a mix of normal and anomalous data. We increased performance by tuning hyperparameters as training progressed. The left side shows the screen where the training is taking place, and the right side is the final hyperparameter learning result. The final learning outcome is 90.6% accuracy and 70.6% recall. Below is a visualization of the AI model's inference results. As you can see, the red shaded areas are the actual errors, and the red dots are where the AI model inferred the error. The video you see was inferred from normal data. The graph on the left is a graphical representation of the model inference results for a hardware chip, which detects errors above a threshold of 0.5. The graph on the right shows the real-time data collected by the sensor board. In this video, we're making inferences from anomalous data. As before, the left side shows inference results, and the right side shows real-time ingestion data. However, what's different from before is the anomalous data. So if you look at the graph on the left, you can see that it infers the error situation. Finally, the concluding part. We worked on a project to build a predictive maintenance system for industrial manipulators. This enables real-time failure and incident prevention, minimizing production downtime and reducing the cost of unexpected failures. Sensor data-driven models can also predict when to replace parts and maximize cost savings, labor savings, and time savings.